So the next speaker will be Filippo Mannucci, who will be talking to us about uncovering double AGNs with adaptive optics.
Okay, thanks for the opportunity to present this ongoing project. Can you hear me and see my slides?
Yes, great, thank you.
Okay. So I presented an ongoing project with Gaia and Keck about dual lens AGNs. So we all know that the galaxies form hierarchically. That means that large galaxies are formed from many merging small galaxies along the cosmic history. And what is true for stars and galaxies is also true, is expected to be true also for supermassive black holes. So each galaxy contributes not only with stars and dark matter and gas, but also with a small supermassive black hole that eventually merge with another small supermassive black hole to give rise to the more massive supermassive black hole. And this simulation shows this effect. These white dots are the supermassive black holes that reach the system together with a small galaxy. And you see that the merging time are long. So you expect to have several supermassive black holes in many galaxies. So given that the merging timescales of these supermassive black holes are large, like 1 giga-year or 10 to the 8 years, you expect to see many or a few of these systems at kiloparsec separations. In most cases, these supermassive black holes are associated to an AGN, so the duty cycle for AGNs is expected to be large. So in many cases, you expect to see dual AGNs, so two different AGNs in the same galaxy at kiloparsec separation. Why is it important to study these objects? First, because this is one of the key prediction of the hierarchical models of galaxy formation, and is still untested. Then we can test the details of the model. For example, the models predict the number of this system as a function of redshift, as a function of separation luminosity of AGNs, for example. And then we can study the process that drives the final merging of these black holes. For example, if the merging is dominated by dynamical friction on the general population of stars, you expect a power law with index of 1 as a function of separation. Of course, then these are the population of objects that will give at the end, when they merge, give rise to the emission of low frequency gravitational wave that will be detected in the future. So it is important to study the parent population. So what is the status of observations? In the local universe, there are a few systems. For example, this is a system in one local galaxy with two AGNs detected in the X-ray. But at high redshift, where the vast majority of the system are expected to be, the situation is much more sparse. Actually, there are only 4 confirmed dual AGN systems at redshift above 1, and with separation below 8 kiloparsec, which means more or less in a galaxy. So this is a current, a recent compilation of objects of dual AGNs as a function of redshift. This is separation kiloparsec. These two lines correspond to 1 and 2 arc seconds, projected separation. And you see there are many objects with several tens of kiloparsec of separation, but below 1 arc second, which means more or less 8 kiloparsec, there are only very few objects, 4 objects above redshift of 1. So to find these objects, you need very high resolution, spatial resolution, but also these objects are rare. So you also need wide field surveys. If you look for dual AGNs, you will also find automatically lensed AGNs. So if you have 2 AGNs, one close to the other, there can be 2 different AGNs, or 2 images of the same AGNs lensed by a foreground galaxy or class, in most cases galaxies. These also are very interesting systems for many reasons, in particular because with this with the lens AGNs, you can sample the structure of the dark matter in the lensing galaxies. So you can study the nature of dark matter. So how can we enlarge the number of dual AGNs? We decided to study Gaia because, of course, Gaia has an intrinsic very high resolution, around 0.1 arc-second in spatial resolution, and it also in all sky survey. So you can really sample all these objects. The problem with Gaia is that the resolution is high, but Gaia assigns for faint objects a photometric window of dimension around 0.7 by 2 arc-seconds. And two objects in the same windows are not distinguished as two objects, are assigned to only one object in the archive. And also, the image is not saved, it only saves the light profile of the object along the Acron-Scan direction. So I won't go into detail, but from the last data release of Gaia, it's possible to study the light curves and see in how many cases you have two peaks, revealing the presence of two objects which correspond to only one object in the archive, but actually there are two separate objects. So we can study the efficiency of this system, of this method, studying crowded fields of stars where you have many apparent pairs. And this is the fraction of recovered stellar pairs as a function of separation. You see the red histogram are the objects that are not recovered by this system. And you see that we don't recover anything below 0.15 arc-second. The black line is the fraction of objects that are recovered by this method. And you see that we have very high completeness, around 90 or 100%. The blue histogram are the objects that are also separated in different entries of the catalog, so we don't really need this effect. But the green one are the objects that are only separated, are only identified within method. And you see that they dominate from 0.15 up to 0.6, and their contribution is important until 0.7 arc-seconds. So we call this technique the Gaia multi-peak GMP. We apply this technique to the spectroscopic targets, to the spectroscopic AGNs, so the AGNs that are observed from, in most cases, from the ground, from the zone. And we have about 250 candidates, which correspond to 0.1% of all the spectroscopic targets. And basically, we can sample this region here between 0.15 and 2.7 arc-second, and where it's where you expect to have the dual AGNs in the same galaxy. Is this technique working? Yes, it works. We have several images of these targets. We have 26 archival images by HST, and in all of them we have two or more objects, two or more components in these objects. Also have 5 dedicated observations with LBT and adaptive optics. And again, in all cases, we see at least 2 objects with separation of 0.2, 0.6, 0.3 arc-seconds. So the efficiency until now is 100%. Of course, if you have 2 objects, you don't know what these objects are. You have 3 possibilities. One is that it's a dual AGN, so 2 different supermassive black holes in the same galaxy. Another possibility is a lens system, so the same 2 different images of the same object, or you can also have a chance alignment of an AGN with a star, with a foreground star. And we expect this system to pollute our sample about 30% if you don't study the spectra or the total spectra of the system. So basically, you need to observe with spatially resolved spectroscopy each of the targets. So we have started this work. We have 8 systems observed, and 4 of them with Keck, with Osiris, adaptive optics. These are the system between redshift of 1 and 2.5, observing a band to observe the H-alpha, with both laser Gaia star and natural Gaia star. And these are the spectra of these 4 systems. You see we see multiple components in all of them. And these are the spectra. You see the spectrum, this is an AGN, narrow line AGN, which alpha and nitrogen 2 with a star. So this is a superposition of an AGN with a star. This is a lens system with 3 images, and the spectra are very, very similar. And these actually are 2 AGN we see with the similar redshift, but very different spectra. So these are really two dual AGN systems, where you have 2 different AGN in the same galaxy. The time delay between these 2 images is at most a few days. So variability cannot explain this difference. These must be real dual AGNs. We have also spectra with different instruments, one archival spectra from HST of a system with 0.46 arc-second resolution. You see very similar redshift, but different spectra. For example, in the fainter object, you see carbon-3 that is not present in the brighter object. So again, this is dual AGN. And also 3 spectra with Muse, narrow field mode with adaptive optics in the optical in this case. And here we have 1 dual AGN and 2 systems with an AGN and a star, a nearby star. So basically, at the end of these 8 systems, 4 are dual AGNs, 3 are pollution with AGN and stars, and 1 is a lens system. So basically, we can start populating this part of this diagram with 4 systems. So we are already doubling the number of confirmed systems, and you see with very small separation in most cases. So the work has just started, of course. So we need to basically identify and observe about 200 systems to obtain 100 or 150 dual AGNs to really starting testing the models. So study, for example, the distribution of separation, the number of objects as a function of separation, or the evolution with redshift. So we need many tens or 100 or more dual AGNs. And we are going on with the observation. We have time at the VLT with Muse to observe 30 targets, and with ARIS, so this is optical instrument, this is a near infrared instruments, with GTO time to observe 120 targets. And we will hopefully go on observing with Osiris to obtain a few tens of targets. So this is a summary. We have defined a very efficient way to select these systems, the rare systems. We have a few hundred candidates with separation between 0.15 and 0.7 arc-seconds. We are going to observe many of them with a spatially resolved spectroscopy to obtain their properties as a function of separation, mass, luminosity, luminosity, and so on, and redshift evolution to test the models. And if you are interested in the details, please check this recent paper that we published on the subject. Thank you.
Thank you, Filippo. Are there any questions? Just a few minutes for that. Questions? So I'm just wondering, I have a question. So could you comment about the success rate that you had between the Gaia candidates and the actual ones that you can confirm with the spectroscopy?
Sorry, what is the efficiency?
Yes.
Well, the efficiency in detecting 2 candidates, two components is very high. Until now, we don't have any counter example. So all the objects are multiple. If we go to spectroscopy, we expect that, let's say, 80% of them are 2 AGNs. And most of these systems are expected to be dual. The models expect the lens system to be 1 order of magnitude less common than dual systems. So at the end, we expect that around 70% of the objects that we observe are actually dual AGNs. With these small numbers, the situation is not as positive. You see that we only have, out of 8 systems, only 4 are dual AGNs. So we don't know if there is some, if we are unlucky in this first observation, or actually the dual AGNs are only 50% of the sample.
Thank you. Unfortunately, we don't have any more time for questions. Thank you again.
Thank you.